The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
All right, our next speaker is Elizabeth Nadelman. She's a PhD student from Department of Civil and Environmental Engineering at Georgia Tech, and she's working with Dr. Kim Kurtis. I just would like to remind our presenter that the screen is being recorded, so if you speak closer to the microphone, that would be great. Thank you.
Thank you for the introduction. I'm going to be talking today about some research that I've been doing over the last year and a half or so, looking at extensions of the surface resistivity test for performance-based mix applications, in particular focus on binary and ternary blends. So the motivation of my work is really these three images. They're all different types of degradation of concrete, but they all have one thing in common. And that's that they all involve the transport of something from the environment into the concrete, and that's what ultimately leads to this type of degradation. So if we want to design concrete for durability, it's very essential that we can also ensure that we're designing it for low permeability. And that starts at the mix design stage. So we need specifically to be able to design concrete that can achieve low permeability, and we need to know that we're doing that while we're designing the mixes themselves. Typically, at the mix design level, most of the tests that are commonly used take a while to do. Like a long-term diffusion test, for example, might take 90 or more days to conduct. And moreover, they provide just a snapshot of what's going on in the concrete. You're only looking at a particular age. What's more important is seeing how that changes over time. So we need a fast and non-destructive method of evaluating the permeability during the mix design stage itself. And that's why I'm focusing here on the surface resistivity test, because it's not only fast, but it's also non-destructive, which means that we can do the same measurements on the same samples over a particular time of interest. So the outline of my talk is, first I'll do a very brief review of the electrical properties of concrete and how they relate both to permeability and reaction rates. A lot of the previous speakers have already covered this, so I'll make that nice and short. And then I'll really focus most of my attention on these experimental results that I've conducted. We looked both at conventional concrete mixtures and also at mixtures that contain limestone cements. So to review, concrete has a resistivity somewhere in the range of about 1 to 250 kiloohm centimeters. And that's controlled largely by the cement paste, the pore solution, conductivity, which is about 1 to 100 kiloohm centimeters. It's right in that range that's typical for concrete. The coarse aggregates are a few orders of magnitude larger, but some of the more or less resistive coarse aggregates will also fall into that range. And so you do see some influence of the coarse aggregate resistivity on the measurements themselves. The fine aggregates are largely far more resistive than the other aggregates in the cement paste, so we don't really look at those as much. They don't play as much of a role because the current will flow along the path of least resistance. Now, as far as that relates to permeability, if you have a very open network, like shown in the figure A, less interconnected, you tend to have a high resistivity. Sorry, I realize there's a typo in there. Less interconnected, less tortuous porosity. It's a lot easier for the current to flow through, the electrons to flow through. It's also easier for water to flow through. So typically when you have high resistivity or low resistivity, you also have high permeability. And the opposite is true with this figure B, when it's more difficult for the current to flow through because you have a more tortuous network, less interconnected porosity. You have a higher resistivity and a lower permeability. And so for this particular project, we're using the AASHTO TP95 provisional standard for the surface resistivity test. And that gives permeability classifications based on the surface resistivity that you measure. If you get a value less than 12, you have high permeability. If you have a much higher resistivity value, it's going to be a lower lower permeability. Now, one of the previous talks also looked at how resistivity varies with time, and that's really the focus of my particular project as well. The resistivity will increase as a function of both the degree of hydration and the secondary reaction rates. So if you have SCMs in your concrete, the rate that those react are going to affect your permeability measurements as a function of time. And so what we're looking at is surface resistivity versus time curves, because that way we can get a better idea both of the degree of hydration and also the influence of these SCMs, how quickly they're reacting and how that affects both the surface resistivity, the permeability, and just the microstructural development itself over time. So for our project, we looked at, to start with anyway, we looked at two different types of conventional Portland cement mixes. The first group, we varied the water to cement ratio from a 0.4 to 0.5 to see what the influence of water to cement ratio would be on these measurements. And then in the second grouping, we looked at mixes that contain supplementary cementitious materials to see what effect fly ash and metakaolin would have. So we looked at 15-25% dosages of the class F fly ash, and then we also looked at a ternary mix that had 25% fly ash and 5% metakaolin. And for these, we kept the aggregates constant, including the mix that had the 0.5 water to cement ratio, because we didn't want to have those affecting our measurements themselves. And these were also cured continuously in lime water. And we measured for 56 days. So when we look at the data itself, what we see is that, first of all, you can see that the ternary mix had the lowest permeability, if you look at the AASHTO classifications on the right side, by 56 days, and actually most of the time. And then the mixture that had the highest water to cement ratio had the highest permeability. And these are pretty typical and pretty obvious to expect. Well, typically these tests are used only at 28 and 56 days to get these snapshots. And so you might see that at 28 days that your ternary mix has the lowest permeability, the highest resistivity, but it doesn't paint the whole picture of what's actually going on. It doesn't tell you what is specifically driving that. Why is that resistivity so much lower at those ages, or so much higher at those ages? So that is why we're looking at these complete curves, because when we look at the complete curves, we see not only what's driving it, we can see when the reactions actually occur. We can see when the secondary reaction of the fly ash starts to occur, around 28 days, for example. Around 4 days, we can see that the metakaolin is starting to react with their pozzolanic reaction. So if we zoom in at the earlier ages, what we see is that at the very beginning ages, the resistivity is largely dependent on how much cement is in the mix. The SCMs aren't reacting very much at this early age, and so really the effective water to cement ratio is what's driving the resistivity measurements we see. What we get is that the ternary mix with the lowest cement content has the lowest resistivity, and that's pretty easy to predict. But at later ages, that's when it starts to become more interesting. We can see, for example, that if we increase the water to cement ratio from 0.4 to 0.5, it just shifts the curve downward at all ages. And that's, again, because there's less cement available to react. We have more open porosity. It's less interconnected. And so we have higher permeability and lower resistivity at all ages. Now, if we add the fly ash, what we see, again, the reaction occurs around 28 days for both mixes, but the rate of that reaction, which is indicated by the slopes of these curves, is roughly proportional to how much fly ash was actually added. So if we were designing a concrete mixture, we could say we want to add, if we wanted to predict how much fly ash would affect our resistivity, we can just look at this and say, well, if we wanted to add 30 or 40%, the slope would just increase even more, and it would be roughly proportional to how much fly ash we add. Now, if we look at the ternary mix, we have not only this fly ash reaction, but we also have the metakaolin reaction, and we see the very high reactivity of the metakaolin at the early ages, which is indicated by this really steep slope. And again, at the later ages, the slope is slightly higher for this mixture than for the two that have just the fly ash, and that's because there's that metakaolin addition. And the slope is roughly proportional to how much, or to the sum of the influence of the metakaolin at this later age, and also the 25% of the fly ash. So to summarize what the conventional Portland cement mixes tell us is that if we decrease the cement content, we get a downward shift of the resistivity curve. If we add this class F fly ash, for this particular case, we got a reaction starting around 28 days, and that the rate of that reaction was proportional to the dosage of the fly ash. And finally, when we add the metakaolin, we get the very high reactivity at the early ages, but then less of an effect at 21 days and later when the metakaolin has largely reacted. So taking this framework now, we decided to look at some lesser understood mixtures, these Portland limestone cement mixtures, and that's sort of a hot topic these days, and a lot of research has shown that limestone cements and fly ash, for example, have a nice synergy where you can get higher strengths and lower permeabilities when you combine fly ash and limestone together. And so what we did was we repeated the same experiment, same mixture, same aggregate types and quantities, but instead we used a type C595 type 1L cement with 10% limestone, and this was coarsely ground, so it had the same particle size distribution as the Portland cement that we were looking at before. And we added fly ash at dosages of 15 and 25%. And again, we repeated the experiment where we looked at the resistivity over the first 56 days. So what we see if we look at the larger trends is that although at the very early ages the mixes that have the limestone have lower resistivities or higher permeabilities, by 56 days we can definitely start to see the benefit of adding the limestone and the fly ash in combination. The synergy is resulting in much higher resistivities at 56 days or much lower permeabilities. Additionally, what we see is that while with the Portland cement mixes, the secondary reaction of the fly ash started around 28 days, it's shifted earlier to closer to 14 days for this mix that has the limestone in it, which is just an interesting thing that we want to look into further. So when we look at the pairs themselves, what we see is that adding the 10% limestone, and keep in mind again, this has the same particle size distribution, it's coarsely ground. What we're getting is a decrease in resistivity at all ages of about 10%. So this has essentially the same effect as increasing the effective water to cement ratio, because we're replacing some of the reactive cement with something that reacts at a less, or reacts to a much lesser extent. Now, if we add 15% limestone, though, we can see again, there's the benefit, the synergy. The reaction starts earlier, as we saw before, but it also occurs at a slightly faster rate. And so what we're seeing is that the limestone may potentially be enhancing the reaction of the fly ash here. And that's suggested by the slight increase in slope. The increase in slope is a lot more apparent when we add 25% fly ash. It increases the resistivity at 56 days by 50%, and the slope is increased by almost that much as well. So to summarize, what we see is that replacing a portion of the Portland cement with the less reactive limestone, again, coarsely ground, it shifts the resistivity curve downward. But when we add the class F fly ash, what we see is that it accelerates the onset of the latent hydraulic reaction and increases the reaction rate. So these have really nice applications for performance-based mix design. If you have a lot of mixes that you're trying to compare to see which ones will get the best performance, or if you just want to see what the effect of different iterations of your mixture are on the permeability, you could do an experiment like this. And so, for example, if you want to look at fly ash, you could see that even though at earlier ages you're decreasing the resistivity and increasing permeability, at later ages you can have increases that are proportional to your fly ash dosage. And you can do the same with more novel materials like these limestone cements. So to conclude, surface resistivity testing is a fast and non-destructive tool that can be used for indirectly assessing the permeability of concrete, which makes it really useful for these performance-based mix design applications where you want to understand how your binder composition is going to affect your permeability and microstructural development with time. Future work would look at how this surface resistivity is related to other permeability assessment measurements, and this has been done quite a bit. But what we notice is when we plot our surface resistivity results with the RCPT results that we got for these particular mixes, while we got a very strong correlation, it's not the same correlation that's been achieved by others. And so this suggests that there's some influence perhaps of the aggregate type or aggregate content that we're looking at that needs to be further investigated in these performance-based contexts. Additionally, there's been work done to relate surface resistivity to compressive strength development. Because permeability, surface resistivity, and strength are all related to the internal structure of the concrete, there's an idea that you can use surface resistivity testing to predict your compressive strength of your concrete. More work will be needed in that area, of course, but if that can be done, then not only can this tool be used for assessing your permeability, but it can also be used to predict strength. And finally, a better understanding of the influence of the aggregates themselves is definitely needed, because we are starting to do some work right now where we looked at different types of aggregate sources, and we found that while the correlations are the same and you get more or less the same behavior, there's a pronounced effect when you change from one aggregate source to another, what your resistivity values actually are. So with that, I'd like to acknowledge the support that I received, the assistance that I received on this project, and I will be happy to take any questions.